Alright, hello everyone. This is going to be a recording of the first day of the F equals MA club. I just want to thank everyone for joining this club. I hope we all enjoy learning about physics together. And so, just a little bit of background about this test. And just generally what this club is going to be about. So, what exactly is the F equals MA competition? This is a 75-minute, 25 question test where the test is going to test about a very advanced interpretation of Physics 1 and optionally Physics C mechanics. And so this is hosted by the American Association of Physics Teachers and the American Institution of Physics every single year. The test usually takes place in February, and this is one of two tests in the USFO competition, which is known as the United States of America Physics Olympiad. And this is going to qualify students for the US International Physics Olympiad team. So this is kind of a pretty big deal if you ever want to get into physics. This test is calculator is permitted, but sadly there will not be a formula sheet. So all the formulas that you have to learn and that I'll guide you guys through, they won't be provided on the test. So what this club is going to be about. So this club is mainly going to be preparing students for the F equals MA competition. And this test is going to be taking place this year on February 9th of 2023, which is on a Thursday. It's going to be proctored by Mr. Simmons, I believe. And yeah, and registration for this test is due on the 23rd of January. And so this club, not only that, but it's also going to teach students who are interested a very in-depth kind of course for Physics 1 and Physics C as well. And so currently, the meeting time is set for Wednesday afternoons. But in the future, if I find it necessary or if everyone really wants to and is very committed to do so, I might add another session or just completely change this current time. And on that note, I just want to remind everyone that this club is in its infancy and to please be patient with me since I really haven't had too much time to get through stuff like the bylaws, like the actual club stuff. I'm still working with the officers and trying to get more. I'm also trying to get advertising and actually getting the material ready. And so, especially with this first meeting, a lot of the material is really difficult, and I kind of regret having such difficult material on the first ever club meeting. So, in the future, a lot of this is going to be toned down. So if you feel really intimidated, don't worry. I'm going to go through all of it as thoroughly as possible. If you have any questions, just let me know. And in the future, if public demand wants me to, I can lower the difficulty, or if everyone feels prepared to, I can even increase it. And so, yeah. So, by the way, I never gave a formal introduction. My name is Joey. I'm currently a junior at the high school, and I will be the president of this club for this year. And hopefully, I'll be able to keep on helping out with this club in future years. So, let's move on to the actual meat of today's little meeting, which is going to be kinematics. And yeah, so this is going to be probably a less known and less seen one as time goes on, since this test is progressively getting more difficult. But it's just nice to kind of get a review, and in case there are like one or two problems that are in the beginning of the test, this will help you get prepared. And so for the kinematics, the most important equations are the kinematic equations. So as we can see here, we have our four very important ones, along with a fifth one, and I can show you guys these right now. So our first equation is going to be, and I think my tablet is glitching out. Just give me a moment. All right. So let's see. So our first kinematic equation is going to be our velocity equals our initial velocity plus our acceleration times time, right? And our second equation is going to be our displacement is equal to our final velocity. Sorry about that. Our final velocity plus our initial velocity over 2 times time, right? Our third equation is going to be probably one of our most important, which is our displacement in x is equal to our initial velocity times time plus 1 over 2 times acceleration times time squared. Our fourth equation, sorry about that, our fourth equation is going to be v squared, which we can also denote as our final velocity, but I won't do that, equals our initial velocity squared plus 2 times our acceleration times our distance. And the fifth one, which isn't shown here, is going to be that our velocity is equal to our distance divided by time. And so these are going to be our 5 very major kinematic equations that we basically need to have in our minds. And so the questions that are going to be on the test are going to just like, they're going to provide a lot of these variables, or at least utilize all these variables, and just require you to find one of them. So say we're given the initial velocity, our acceleration, and our time. We can use this first equation to find our final velocity, or our velocity after a certain amount of time. If we're given the acceleration and our velocity and our total distance, we can use that to try and find the time, and these can be used for many other cases. And so going back, we can start off with our first example, which to be completely honest, I think is a little bit harder than most of the other problems in here. But it's from the 2013 F equals MA exam, and it states an observer stands on the side of the front of a stationary train. When the train starts moving with constant acceleration, it takes 5 seconds for the first car to pass the observer. How long will it take for the 10th car to pass? And if you guys want to work on this on your own, feel free to do so, and you can just pause the video here and resume it once you're ready. All right, and I'm assuming that if you actually tried to do this, you're probably resuming the video at this point, and if you're just watching through, that's completely fine. And so this is one of the more challenging ones that is going to be on here. So let's start off with trying to draw a diagram of what's going on, which is going to be one of our main steps and tips for the exam, which is that a lot of problems are going to have some really weird or really funky wording, and how to combat this is to just draw a diagram and try and figure out what's going on. So we currently have, what is this, 10 trains, right? 10 train cards. Let's label these 1, 2, here we go, and let's draw these fully, and then we can have like 3, and then we have a lot more, and then we have something like 9 and 10, right? So right now we know that the observer is standing around here, and they're looking at the train from here, right? And so the train is moving at constant acceleration, right? And so we know that the time that it takes for the first train car to pass is 5 seconds, right? And now we're being asked how long it takes for the 10th train car to pass. All right, and if you just wanted a hint, this is going to be your hint, and the full solution is about to start. Oh, and I just realized that my little slideshow is actually covering this, so I'm just going to hide that for a moment, and you can see the full diagram. All right. Sorry about that. So let's move on to the full solution. So for this equation, at least for this problem, we have we can use the equation which is delta x equals our initial velocity times time plus 1 over 2 times at squared, right? Where this is our acceleration, this is our time, this is our velocity, and this is our distance, right? So from here, we can substitute this x for the length of the first train car, right? Because that's the information that we're given. So let's denote this as, let's say, C, right? For car, because I'm very creative with my naming choice. So we currently have C is going to be equal to, and we know that our initial velocity is equal to 0 because this starts from rest and starts moving at constant acceleration. So we know that this value is going to be equal to 0. And so now we know that C is just equal to 1 over 2 at squared, right? We currently have our t here, right? We just don't have our a and our c. So what we can do here is we can just move these across and just take these with variables. So we can say 2c over a is equal to t squared, right? And in this case, for our first train car, this is going to be equal to 5 squared, which is equal to 25, right? All right. So from here, let me see if I can resize all this. And I can, what was the tool? I think it was this one. Move this across, and we can move this up. All right. And from here, now the question is, what do we do with this information? We currently have the information of 2c over a is equal to 25 seconds. And so from here, what we can do is we're trying to find the time it takes for the 10th car to pass, right? So a method of doing this is we can measure the amount of time that it takes for 9 train cars to pass, right? So we can say, let's just say this is a train, right? And then this is our 10th train car. So this is 9 train cars, right? This is 9 train cars. No. This is 9 train cars. 9 train cars. And this is 10 train cars, right? 10 train cars. And my handwriting is beautiful today, if you couldn't tell. So what we can do is we can measure the amount of time that it takes for 10 train cars to pass. And then we measure the amount of time that it takes for 9 train cars to pass. And then if we subtract these, the remaining amount is the amount of time that the 10th train car takes to pass, right? And so that's going to be the basis of how we solve this problem. Let me just erase this little chunk. Should have just moved it. Yeah, all right. So with that information, we know that we need to find the amount of time that it takes for 9 train cars to pass. 9 train cars to pass. Not L. Why do I keep on writing L? 9 train cars to pass, and we need to find the amount that 10 train cars take to pass. Right? And then we need to subtract these from each other. That's the entire basis of what we're doing. So, how do we do that if we don't know the lengths of our train cars and we don't know the acceleration? What we're going to be doing here then is we take this equation again, right? And now we know that our length, the length of 9 train cars is going to be 2 times 9 train cars, right, over A is equal to, let's just say this is T2 squared. And the time that it takes for 10 train cars to move past is going to be 2 times 10 train cars, right, divided by A is going to be equal to our third time squared, right? And so from here, we can say that this is, and if I zoom this down even less, because I'm really good with space management, let's just move this through, because that was very clean. No, my 2. Anyways, no, I'm very bad with Krita. with this information down, what we can do from here is we know that this is 18. No, no. This is please. Thank you. We know that this is going to be 18c over a. This is going to be 20c over a, right? But we can actually rearrange this in a different way, where we can say that this is 9 times 2c over a, right? And this is 10 times 2c over a. And we know right now that 2c over a is equal to 25, and that's shown here, right? So we know that this is going to be 9 times 25 is equal to t2 squared. And we know that 10 times 25 is equal to t3 squared. And so to actually find t2 and t3, we just need to square root both sides, right? We just need to square root both sides. And our answer for this is going to be t2 is equal to, I think this is 225, right? So square root would be 15 seconds. T3 is going to be equal to the square root of 250. And if I just plug that into my calculator, the square root of 250 is going to be around 15.81 seconds. 15.81 seconds, right? And so now we just need to find the difference between T3 and T2. So T3 minus T2 is going to be equal to 15.81 minus 15, which is equal to 0.81 seconds. And with what I previously mentioned, we now know that this is the amount of time that it takes for the 10th train car to pass. And if we just double check on our slideshow again, we see that there is only one solution that is 0.81, and that is going to be E. I can't pronounce things. So yeah, that's how we do this problem. I know this was a lot more challenging than some of the other ones, but starting off with a very fresh start. So yeah, so that's going to be a general introduction to the basic kinematic equations. And so moving on, we can start talking about projectile motion now. And so there are two very important equations for this, measuring the x position and the y position of a projectile at a certain given time. And so if we go back to this screen where I can actually draw, we're going to have, what is this? We're going to have x of t, that's the wrong color, let me choose a different one. We have x of t is equal to our initial position, our initial x position, plus our initial velocity times time, times cosine of theta. And I'll get into how that works, right? Oh god, okay. I need to learn like how to write these in the right place. Just give me a moment. I'm having a hard time. Let's move this over here. Can you guys see that now? Yes, you can. So let's go back here, cancel that, and go here. So this is going to be our x position over time. And our y position over time is going to be equal to our initial y position plus our initial velocity times time times sine of theta, minus 1 over 2 times gt squared, right? And so how this works is, let's denote this right now. So let's say we're just on the ground, right? On the ground, we have a projectile being launched at this angle, right? We can say that this is theta. So let's think about every component of this. First, we're going to have our x component, right? And the interesting part about the x component is that there is no horizontal acceleration. There is no horizontal acceleration, right? And hopefully you guys already learned this. So there's no horizontal acceleration, which is why there is no like minus at squared here or anything like And so this is going to be our initial velocity, right? This is our initial velocity times time times cosine of theta. On the other hand, we have our y component, which is going to be up, right? And so this is going to be denoted as vt sine of theta, right? And these are going to be the components that make up this, right? So we can say that these two components make up the actual velocity times time, right? And for our x, we can say that this is vt cosine theta. All right, so the one thing that sets the y position from the x position apart, other than the sine and cosine, is the fact that there is an acceleration, which is going to be denoted by g, which is going to be a gravitational acceleration. And on the test, this is going to be very important. On the test, g is always going to be equal to 10 meters per second squared. There's no 9.81, 9 point whatever the rest of it was. And so this is going to be really convenient for most of our calculations. And so these are going to be our two main equations for projectile motion. And now, since we have all that down, we can start with our first practice problem about projectile motion. So this is from the 2015 exam, question number 5, which says a 470-gram lead ball is launched at a 60-degree angle above the horizontal with an initial speed of 100 meters per second directly towards a target on a vertical cliff wall that is 150 meters away, as shown in the figure. So the question is asking, what distance does the lead ball miss the target when it hits the cliff wall? So if you want to work on this on your own right now, you can pause the video. And if you finish, or if you just want to know the answer, we're going to start right now. So let's go here and switch our scene. So currently we have, what is this? So we have a ball being launched, right? We have a lead ball that's being launched from the ground up. That was a very straight line. Very straight. I'm having a hard time today. I'm having a very hard time today. So, we have a lead ball with a certain mass that's being launched up at the target, right? This is going to be our target. This is being launched at an initial velocity of 100 meters per second, right? And this hypotenuse, this length, is going to be equal to 150 meters, right? And so if you just came here for the hint of what's generally going on, that's your little hint. And so remember that our ball, because of gravity, is going to start moving down a little bit. And so when it actually hits the wall, it's going to hit around here. And so this problem is asking what this distance is. And if you want the full solution right now, here it comes. So let's just erase all this and start getting back. Straight back. All right. So let's start working this problem, shall we? There's two really cool ways to do this. One is the way that I just showed you, and the other way is absolutely ingenious, and I will show that in a moment. So right now we have what is essentially a triangle, right? We have that this is a great triangle. This is an absolutely wonderful triangle. So we have a triangle, right? We have a triangle that looks a little bit something like this, where I'm definitely not cheating with the line tool, where we have a theta, which this is definitely not drawn to scale, but this is going to be 60 degrees, right? This is going to be a right angle. And so for anyone who has ever taken a trigonometry class, we will immediately understand that this is a 30, 60, 90 triangle. This is a 30, 60, 90 triangle, right? And so what this means is that the ratio of the side lengths is going to be 1 to the square root of 3 to 2. And so if we write that out right now, that means that currently our hypotenuse is 150 meters, right? That means that this is going to be 75 square roots of 3 meters. and this is going to be 75 meters. I know this diagram is deceptive. I'm sorry. So our given information is that our ball has a mass of, what is this, 470 grams? 470 grams, right? And it's fired at an initial velocity of 100 meters per second. And let's just write out our projectile motion equations just to have this be a little bit more convenient. And so the first thing that we can see is that our mass definitely won't matter. Mass doesn't affect anything from this equation, and so we can just ignore that. That's typically used as just something to throw off people on the test who don't have too good of an understanding of physics. And so from here, that was not intentional. So we know that this is basically irrelevant for now, and what we really need is this velocity, and basically these equations, right? So let's just shrink all this down a little bit and move it to this. That's not what I meant to do. And move this a little bit to the side. Make this a lot more convenient for me to write on. So let's just make this a little bit smaller, and just move it there. All right. So first thing that we need to do is try and find the time, and that's typically what we do in these type of problems. So we know that our x position and our y position are basically irrelevant here because we can just set this to 0 and just move on. So our big thing is just going to be trying to find our time and trying to find our y. So currently we know that our x is going to be 75 meters, and that was shown by the triangle here. So we know that 75, I should change the color. We know that 75 meters is going to be equal to our initial velocity, which is 100, times cosine of 60 times time. And so if we do this, 100 cosine of 60 is going to be equal to, and if I get this right, no, that is not right. Okay, anyways, this is going to be 1 over 2, right? So we know that this value is going to be 50, and if we just divide both sides by 50, we know that our t is going to be equal to 1.5 seconds. Our t is going to be equal to 1.5 seconds. Okay, from here, we can plug this into our y equation, which is y of t is going to be equal to our initial velocity, 100, sine 60, minus 1 over 2 times 10. Remember that g is equal to 10 meters per second squared, times 1.5 squared. And if we were to plug this all into our calculator, we would be getting around let me see. Hold on just 1 minute. I don't know why. I think I did this wrong. Oh, sorry. I forgot to add that this needs to be multiplied by 1.5 as well. So this, let's just change this a little bit. You know, I really would just do better if I just undo. So this is going to be multiplied by 1.5 minus 1 over 2 times 10, as told before, times 1.5 squared. Well, I'm just not in a good mood today. So this is going to be 100 sine 60 times 1.5 minus 5 times 1.5 squared, right? And so this is going to give us around, I think, 118.65. We don't need to be that precise. But that's where our y value is going to be. So it's going to be around there, right? And so the height that our that our line reaches, that our target is at, is around here, and its height is going to be 75 square roots of 3, right? So that is going to be around 75 square roots of 3 is equal to around 130, right? It's around 130. And so what we do right now is we try and find the distance between them, right? So it's going to be 130 minus 118.65, and that is going to be equal to that is going to be equal to around 11. Yeah, this is going to be equal to 11 point like 35 or some crap like that. It doesn't matter. It's around 11, and we only have one answer choice that's close to that, which is going to be 11. And so this is one way of doing this, and the other way is incredibly ingenious and much smarter than whatever the hell I just did. And this is done as such. So let's assume that we're just firing this projectile on the ground, right? We're firing this projectile on the ground. There's nothing affecting it, and this is just shooting across, right? So we have a projectile that's launched here. Is told to be launched at a distance of 150 meters, and it's fired at a velocity of 100 meters per second, right? So what's the amount of time that this takes? So we can technically just use one of our equations and just rearrange this a little bit. So our t is going to be equal to our d over v, which is going to be equal to 150 over 100, which is going to be 1.5 seconds. And we know that this works because no matter what, our horizontal velocity is not going to change because there's no horizontal acceleration as said before. So this time is still going to stay the same. And the other thing is that the only thing that's going to change between here, this change is due to acceleration. And the only factor that changes it is this part of the equation, right? And so what we can do is we can just plug in 1 over 2 gt squared and plug in our time, which equals to 5 times 1.5 squared. And if we just plug that into our calculator, that's going to be around 11.25. Not around. It's going to be equal to 11.25. Basically same answer as before. It's still at 11, and it gets the same answer in a much smaller amount of time. And this just shows like the kind of like advanced interpretation of physics that the F equals MA competition is going to require, where you need to take everything and kind of interpret it in a very advanced and very just like second level kind of way. And yeah, so that's going to be our question for this. And now we can move on to our second projectile motion question. So this one's going to be a little bit easier than the other one. And I can just sketch it out right now, since this is already going a little bit over time. So we currently have 2 cannons that are firing, right? We have one above and one below. And if you really do want to look at it, the slideshow is going to be in the folder. So these are spaced 200 meters apart. Again, I'm great at drawing lines today. This bottom cannon is going to be firing upward at a velocity of 25 meters per second. This upper cannon is going to be firing downward at a velocity of 55 meters per second. This question is actually 2 problems. The first part of this problem is what is the time? So at what time do they collide, right? So we're trying to find t when they collide. The second portion of this problem is finding how far below the upper cannon the objects actually collide. So what is this distance, right? What's this distance, right? All right. If you want to solve this on your own, basically the clue is already here with this part. So you can just pause the video and do it on your own. Otherwise, we're gonna get straight into it. So we currently, I don't know why I erased that. We currently have our 2 cannons that are firing, right? Let's label these, I don't know. I'm too lazy to actually label them. So the really convenient thing about these is we can simplify our projectile motion equations. First thing is we have no horizontal displacement, right? Our our projectile isn't going to go, I would like to go in this direction now. Screw you, Joey. So that's one convenient thing. The second convenient thing is that technically our angle is sine of 90, right? Our angle is going to be 90 degrees, and sine of 90 is going to be equal to 1. So for our y equation, y of t, this is going to be equal to, as we said, our y position plus our initial velocity times time times sine of theta. But we can just completely remove this from the problem because sine of 90 is equal to 1, and this is just 1 times the initial velocity times time. And we have the minus 1 over 2 gt squared stuff. Okay, so let's start working on this problem then. So let's denote these, the y positions for all of these, for these two cannons, as y1 for this one and y2 for this one, right? Convenient naming. And so let's start solving for these, right? Oh god, I should really color code. So let's say that this is y1 and this is y2. All right, let's go. So for y2, our equation is going to be, and remember that this is 200 meters above the lower cannon, right? So we can set the initial y position to 200. And since our velocity is pointing straight down, and velocity actually has a direction, god, okay. If there was like a portion of that video where like you literally could not see anything, I'm so sorry. I forgot that I had the slideshow still up here. I'm gonna go hide that now. If you really couldn't see that, basically what I was saying was, we have no horizontal displacement, and our sine is going to be equal to 90, which is equal to 1, which means that our equation, which is going to be y of t, is equal to our initial plus vt sine theta minus 1 over 2, minus 1 over 2 gt squared. This can be eliminated because that's 1. So that's a really convenient part about this. And I am still moving this incorrectly. Let's just move this over a little bit. Never mind. I guess I will not. Yeah, so sorry guys. This is the first time I'm doing this. Okay, is that better? Yeah, that's better. So wow, I'm already going very much over time. So we're starting with this equation, right? And so I'm just going to erase this. And so we can start from here. Our y2 of t is going to be equal to our initial position, right? Here, which is 200 meters, plus our velocity down, which is 55 meters per second. And remember that this is going to be negative since this is moving down. So let's just erase that part. This is going to be equal to 200 minus 55 times t, and then minus 1 over 2 times g times t squared, right? All right, and now we can move on to our y1. And our y1 is going to be y1 of t is equal to, and our starting position is going to be 0, so this is 0, plus, since the velocity of this is moving up at 25 meters per second, we're going to have 25t minus 1 over 2 times 10 times t squared. So right now we're trying to find when these two projectiles collide, right? And when they collide is going to be when these two equations are equal to each other, right? Because that means that their time is the same and their position is also the same. So let's write this out. So 25t minus, let's just simplify this to 5t squared, right? It's going to be equal to, 200 minus 55t minus 5t squared. So the first thing that we can do is, off the bat, we can just cross these two out. These are the same, so we could just add one of them on the other side and just cancel them out. Next thing we can do is we can move this. We can move our 55t over to this side. So now we have 80t, 8 please, 80t is going to be equal to 200, right? So our t is going to be equal to 200 over 8, which is 2.5. 2.5 seconds, right? And if we look back on our slideshow, which I forgot to show, my bad, we have the answer of 2.5 seconds, and that's going to be B, right? And so our next question is, how far beneath the top cannon do the projectiles collide? So what we can do here is we know that we're going to have, we can just plug it straight back into this equation, right? And since this is just going to show the position relative to this cannon, right? We're going to have to do 200 minus all of this, which is going to be really inconvenient because we have 200 two times. So what we could write here is, if I can zoom this down with my very big brain, let's move that over here and make this smaller, right? Okay, so back here, we can plug this straight into 200 minus y2 of, what is our t? 2.5, right? This is going to give us the position, right? Below the top cannon. Yeah. And so the thing about this is we're going to have an equation which is 200. I don't know why I'm writing my 2's like this now. 200 minus 200 minus 55 times 2.5 minus 5 times 2.5 squared, right? And this is really inconvenient because we can literally just cross these two out, remove this, and just make these two positive, right? That's how math works. So now we have 55 times 2.5 plus 5 times 2.5 squared, right? And if we just plug this all in, 55 times 2.5 plus 5 times 2.5 squared, 2.5 squared is going to be equal to 168, please, 168.75 meters below this top cannon, right? And so if we look back at our slideshow one more time, we can see that this is closest to E, which is 170 meters. So yeah, that's going to be our projectile motion, and this is basically the material if you've ever taken Physics 1 or Physics C mechanics. You know these. These are really easy. This is cakewalk, or whatever the expression is. Piece, pie, whatever. Yum. I'm hungry. Anyways, this is where the little f equals ma, little tricks and little equations come in. And these come in the form of these three equations for projectile motion, which is time of flight, our maximum height, and our horizontal range. And I can show you a proof of this right now, and I know we're running out of time, and if you don't want to listen to this, you can just skip through. This isn't required. I'm not going to quiz you on this later, but if you are really curious, just listen. So let's first try and find the time of flight, right? So, how do I do this? So, v squared sine theta equals, oh, yeah, so this follows a very basic principle of projectile motion, which is that the time that it's going to take for an object to fall down is going to be equal to 2v over g. And the reason why we know that is because, if we think about this, our velocity, our velocity, if we were to throw this straight up and then straight down, right? The amount of time that it takes for the object to go from here to here is going to be our velocity divided by g, right? And so if we want to know the total amount of time that it takes for it to go up and down, it's going to be this equation multiplied by 2. And so that's how we get 2v times g. And if you want a more detailed explanation, you can just let me know. And so, with this equation, we know that our prerequisite, which is that t, nope, that's not what I want to do. T is going to be equal to 2v over g. And since we can just use it for our and so the problem with this is that this is for free fall only, where our sine is automatically equal to 9. Our angle, sorry, our angle is automatically 90 degrees, right? Oh God, no, I forgot I have the thing up. I'm so sorry if you couldn't see before. Yeah, I'm working with this right now. So 2v or you know what? I should really just like put a box here and just remind myself every time. So this is only applicable when our angle, please work with me. Oh no, please, no. Okay, finally. So this is only applicable when our angle is 90 degrees, right? Because sine 90 is equal to 1, right? So this is applicable. The problem is, sometimes, like, for projectile motion, we're going to have different components, where a portion of the velocity, if it's not, like, throwing straight up or straight down, a portion of the velocity is going to go for the x component. Not all of it is going to go for the y component. So, in order to find the amount for the y component, the actual velocity that's going up and down is going to be, v initial sine theta, right? And we can set that equal to the v that is present in this equation. And so, based on that, now we know that t is equal to 2v sine theta, and this is initial, over g. And that's where our first equation comes from, right? So that's one equation down. I'm going to erase all this, and yeah, most of this. And now I can go here, move this up here, and we can continue with our lesson. Next, let's go for the maximum height reached. Y max, right? That's my eraser. Y max. And so how we're going to prove this is our maximum height, right? Our maximum height is going to be equal to, this is also another equation that you just need to know off the top of your head, which is v squared over g, right? That's going to be our maximum height. And again, with the same logic as before, we're going to set this v to v naught, or the initial velocity, sine theta, right? And so that means that our y max is going to be equal to v squared, or initial squared, sine squared theta over g, right? Oh, and this is 2g. I'm stupid and also very much not awake. So, yeah, that's going to be our second equation, right? And so, let's just big eraser. Let's go here. I'm smart. This is y max. And let's use this. No, okay. This is gonna get annoying. Let's use that. Move this over here. All right, and that's our second equation, right? And now our third and final please. Okay, our third and final equation, which is going to be less appealing, but it's probably going to be the most complicated, in my opinion, at least. So we have our x max, right? And we can just set this to x of t is equal to our initial position, which is going to be 0, times our velocity, our initial velocity, times t times cosine of theta, right? That's our equation. Plugging it in from here, now we have v naught squared times 2 times sine of theta times cosine of theta over g, right? And here's where the pre-calculus comes in, which you never expected to happen, which is that sine of 2 theta is going to be equal to 2 sine theta cosine theta. With this information, now we can simplify this to 2 v naught squared times sine 2 theta over g. Actually, no 2. And that's where our third equation comes in. And if we look back at our very handy dandy little slideshow, we can see that that is very much true in this scenario. And if you want to double check, please do, because I'm not even sure if I did it correctly. All right. And from here, we can move on to our next portion, which is going to be a question from the 2012 F equals MA exam, question number 2. And you can see what I mean by these are pretty much going to be like the introductory ones that aren't going to be seen too often anymore. All these questions are plucked from very early tests and from very early questions from these tests. And so this asks, basically, if I were to simplify this, it's the angle where h is larger than r. And if you want to pause the video and do this on your own, please do so. If not, we're going to start right about now. So let's write out this problem, right? So we have a cannon that shoots a projectile at a velocity, at a given velocity, right? Please work with me. Please. There we go. Okay, now it's working with me. So we have a velocity, right? And we're trying to find the angle theta, the minimum angle theta, where our height is greater than our range. And so how we're going to go about this is we're just going to say that the minimum angle is where h is equal to r, because any angle that's higher than that is going to be where h is greater than r. And that can be inferred through common sense. And so let's just take those equations from before, where we have v squared sine squared theta, I'm just going to write it like that, over 2g is going to be equal to our v squared sine 2 theta. Did I do this right? Over g. I'm just going to double check. Yeah, that sounds about right. Because it is. Okay, good. And so now what we can do is we can simplify this equation a little bit. We can cross out these g's first of all, and we can also cross out these v squares. So now we have sine squared of theta over 2 is equal to sine of 2 theta. And that's going to be our minimum angle. And here's where our second very important tip for F equals MA comes in, which is if you have the chance to, whenever possible, just substitute the values. Everything in it is multiple choice, so just substitute values when you can. And in this case, we absolutely can. And so if we were to substitute our values, we would see that our very first value is going to be our valid value, which is theta min is equal to 76 degrees. And we can do that if we just look at the slideshow, not that slide, the other slide, and we can just plug in all those values until we get one that looks reasonable enough. All right, and so that's going to be our little advanced projectile motion question. And so here is the point where I regret everything for making this slide, because for anyone who hasn't been in calculus before, these next few slides are going to start getting really difficult really fast. So let's first switch over to slideshow only. Okay, so now it's time to get ready for some learning Physics 1, kids. And if you haven't learned any calculus yet, this is going to be even better. And if you really want to know what's going on, please just go online, search up what a derivative is, search up what an integral is, and please do the research on your own, because I'm not qualified to teach. You know what? I'm not qualified to teach any of this. I don't know why I'm here, but I am, and I'm the president. I don't know what happened, but we're just going to continue on without my existential crisis. So get ready for some Learning Physics 1, kids, because it's going to get really fun from here. Don't mind that part. So this is the part where interpreting graphs comes in. And I'm just going to show this slide for a moment. If you want to pause and look at it a little bit more, you may. But we're just going to get straight into it. So, there are three main types of graphs that you're going to need to know. And they're all based on time, which are position versus time. Position versus time. We have velocity versus time. And we have acceleration. Acceleration. I understand why Khan Academy does that. Versus time. And so these are going to be the three that you need to know. And it's time for the calculus, baby, because there are actually very intricate relations between these. And to pull out the calculus terms, the derivative of position is velocity, and the derivative of velocity is acceleration. On the other hand, the antiderivative of acceleration is velocity, and the antiderivative of velocity is position. And I know, like, anyone who has never taken calculus before has just went, what the hell are you talking about, Joey? Why am I here? Please kill me. And so I'm going to simplify this a little bit with a nice little graph. So let's say this is our this is going to be falling straight from the interpreting graphs. So let's say we have, this is our position graph, right? This is our position graph. Please learn how to, okay. So this is our position graph. This is our velocity graph. And this is our acceleration graph, right? Where, oh, this looks so bad. You know what? Let's just draw these normally. So let's draw this all on one axis because we love frying your eyes. So this is going to be our position, right? This is going to be our our velocity, and this is going to be our acceleration. And I can label all of these accordingly. So what does this all mean? What the hell's a derivative, and why am I still here? So the very base definition of a derivative is the slope of a graph at any point in time. And this is also known as the instantaneous or whatever. And so let's say we want to find the slope of this x. And let's say that this x, let's say x over t of t is equal to, I don't know, like x squared. Let's say it's x squared, right? That means that the slope at any point in time on this graph is going to be 2x. And so a much easier example is that the slope at any point in time on this velocity graph is going to be equal to 2, right? Because the slope of 2x is always going to be equal to 2. And I really hope that you've at least learned slope-intercept form to know that, because if you haven't, please go learn that and come back later. So now we know that our derivative is a slope, and the antiderivative, in its most basic definition, is going to be the area of the graph, right? So let's say we have this, right? Let's say we have a graph that looks like this, right? Oh, please. We have. Oh, why is it white? We have a graph that looks like this, right? We have a graph that no. We have a graph that looks like this and goes down here. The area, or like at least the antiderivative, starting from here to here, is going to be the area of this portion, right? And the antiderivative from here to here is going to be from here to this portion. So let's say, hypothetically, I were an evil physics teacher, person making the exam, right? And I asked you, given this velocity graph, velocity over time graph, calculate the change in position, let's just say, from, let's say this is, like, I don't know, this is 1, right? And this is a straight line. And this goes down, right? And this is like 2, and this is 5, right? And let's say I want you to tell me the change in position of an object with this velocity graph from 0 to 5. And so how you're going to calculate that is you're going to have to find the area of this, right? So this is going to be 1 over, no, this is going to be 1 because 2 times 1 times 1 over 2 is equal to 1. And this portion is is 5 minus 2 times 1. So this is going to be 3, this is going to be 1. 1 plus 3 is equal to 4. So our change in position is going to be 4. And so here's where the funny, like, actually, like, painful stuff is going to come in, which is power rule and stuff like that. And I would really recommend you just search this up. It explains it in this slide. Please, just search it up if you don't know calculus. Power rule, where, like, if you have 2x, that, what in the world? So if we have our equation of 2x, the antiderivative of this is going to be equal to, or, okay, let's just write the general rule. I'm sorry, I did not prepare a lesson plan. So let's say we have x to the n, right? The antiderivative of this is going to be equal to n times x, n minus n plus 1 times 1 over n plus 1, right? And the reason for this is like the actual power rule, because I used the wrong term. So this is for antiderivative, right? This is for antiderivative. For derivative, if we have x to the n, our derivative is going to be n times x times n minus 1. And so these are like the two really important things that you need to know. And I realized on my slideshow is once again covering this one. So just pretend that there's a 1. There's a 1 here, right? Okay, so that's calculus. Please do research on your own if you don't know calculus yet. Yes, please go do that. And then yeah. So from there, we also can use that to determine like minimums and maximums, and I would also recommend you do that research on your own. Since I'm already 1 hour into recording, I am not re-recording this, and I'm not teaching the entire like first three units of calculus in a physics video. And to quote my physics teacher, this is why I'm not a math teacher. Though that was used for a very different context. Anyways, that was an intentional voice crack, by the way. Once we understand maximums and minimums, we can move on to this problem from the 2010 F equals MA exam, questions 1 to 3, which is, given this graph without a specified y, and given that y on multiple questions, what is the greatest speed? And so this is, you can pause the video right now and just go over this on your own. And if you have finished doing this, or you just want to get the answer, here I go. So we have a graph that I'm bad at drawing graphs, but and I'm also getting too excited. So let's say line tool. I'm not bothering with like drawing properly. Let's say this is our line graph, right? What does this line graph look like? So we start from here, we move up, right? We move up, and then we go down, and then we move back up again, right? Is that what the graph looks like? Yes. So we have different points here, right? We have A, we have B, we have C, we have D, and we have E. And this is always by time. So, first question. Given that this is a position over time, so this is x, where is the greatest speed achieved? And so one of the big things that we need to cover again is that we have the whole relation where x, v, and a, or position, velocity, and acceleration. This is going to be the v is the derivative of x, and a is the derivative of the v, and we also have the other side. And so the thing about speed is that in the most simple terms, velocity, this is probably a definition that everyone knows. Velocity is a speed, it has a speed and a direction. And that's a really important thing, right? You can have negative velocity and like velocity in this direction, or like, I don't know, this direction or something. That's what velocity is. Speed, on the other hand, doesn't have a direction and will always be positive, essentially. And so, let's interpret this graph, right? So, where is the greatest speed achieved? And if I were to write this in mathematical terms, our speed is equal to the absolute value of our velocity. Or I don't know. That's probably a really bad explanation. So where is our velocity, where's our speed the greatest? And to answer that, it's going to be from B to D, because this is the part with the greatest slope, right? This is, like, I'm assuming, like, -2, and this is 1. Let's just say that. This is 1, this is -2, this is 1. This has the greatest speed, because the slope, right? We're talking about slope right now. This is the derivative, right? Here's where the slope is greatest, right? That means that our velocity is greatest there, because that means that our slope, or our derivative of our position, is greatest, and that has the greatest magnitude, at least. The absolute value of -2 is greater than the absolute value of -1 in the most mathematical way possible. And so the next part of this problem asks, okay, now we have position, right? What if we make this into velocity? Where do we have the greatest speed? And once again, I need to reiterate that our speed in this case is going to be the absolute value of velocity. So if we were to redraw this graph, we could say something like, this graph would look something like this for speed. I don't know, something like that, or something, I don't know. I don't care enough right now. No, like that. Anyways, I'm sorry, I'm very tired right now. So, that means that our greatest points, our greatest speeds are going to be at B and D. And only those 2 points, right? Because this is just velocity. This is just essentially getting the y value, and which y value is, which absolute value of the y value is greatest. And that sounds really confusing, but you'll understand, because these 2 values are basically the furthest away from this straight line, right? And so now we have that, and the final question is asking, if this were the acceleration, what do we do? Where is it the greatest? And this is where the antiderivative stuff comes in, where I was talking about area, right? So, at what point is the speed the greatest? So we need to understand that once we get here, this is actually going to be negative area, right? We're going to be subtracting this portion of the area from here, right? So that means that our greatest speed is going to be at point C, because from point C onwards, we're always going to be subtracting. Our speed is going to be going down, because our acceleration is now negative, right? Which means that the slope of our velocity is negative, which means that it's going down. So that's the basis of these 3 problems, right? And it's a lot more simple if you actually understand what's going on. But the thing is, again, I'm not a math teacher. I'm also not a physics teacher, but I'm trying my best. And so, moving on from here, that's basically these 3 problems done. And now we have the very rare, but very commonly seen in other fields question, which is known as the relative motion question, also known as the riverboat problem, because physicists and, like, problem makers are very creative, and obviously, they always change the prompt. They do, of course. So, the riverboat problem is as follows. Say we have a river that has a certain current, right? And we have a boat that is trying to row across, right? Let's say that this boat has a certain velocity. And we can say that the river has a certain velocity, right? Its current has a certain velocity. So, the basis of this problem is, what is the relative motion of the boat, like, in regard, like, if you were looking at the boat from the land, what would the relative velocity be? And what would the direction be? And so, this is what it would be. And if you couldn't tell, this slide took up basically 95% of my animation budget. And so, what this is saying is that given that we have a velocity pointing in this direction and a velocity pointing in this direction, we can combine these together to find the final actual or like relative velocity in regards to looking at the boat from land. And if you were in advanced math, I would probably say some crap like, this is vector addition. Yeah, because that's what it is. But I'm not going to use the fancy terms because I'm not fancy myself. And so that's basically how you do this. And in order to solve this, if we just switch back to my scene, if we are given the direction of these two vectors, let's just say it's moving in this direction for one and moving in this direction for the other, we know that our final velocity is going to be like this. And how do we find that out, you might ask? Well, the thing is, typically, these people aren't actually creative. So, usually, it's just a boat moving in some direction and a current moving 90 degrees to that other direction. So we can use some very quirky theorem that I hope everyone here knows, which is the Pythagorean theorem. A squared plus b squared is equal to c squared, where we can say this is our a, this is our b, and this is our c, right? And so now we can find this, and using some even more quirky maths, we can try and find the angles given our two sides, right? So that's the basis of this problem. However, the F equals MA competition, as I've shown before, is very creative. They have very interesting twists on these very basic concepts, and so we see that in this next problem. And I'll probably give a little bit more time, or like I would recommend you take a little bit more time on this one. So this is from the 2015 F equals MA question number 1, which states that a 600-meter wide river flows directly south at 4 meters per second. A small motorboat travels at 5 meters per second in still water and points in such a direction so that it will travel directly east relative to the land. And this asks for the time that it takes across the river. And so this is a really interesting problem, and I recommend a lot of you to just try this out and see how it goes. And if you're done, or if you're just still here and didn't bother to pause the video, I'm just going to start solving this. So let's go back here. So we have a boat, right? We have the boat that's pointing in a certain direction, right? We don't, like at a certain angle where its velocity is 5 meters per second, right? And the current is 4 meters per second. And it's at such an angle that the relative motion is going to be in this direction, which is really interesting because typically what we do for these relative motion problems is that we're given these two legs and we're told to try and find the hypotenuse, right? Which is the relative motion. But in this problem, we're given where the relative motion is going. We also know the lengths of these legs, right? We just need to find how long, no, we're given this. We're given the hypotenuse, actually. Sorry, I'm writing this incorrectly. So we're given the hypotenuse, right? We're given the current speed. We, in this case, we need to find the leg. This leg, right? That's what's really interesting about this problem. And if we know anything about Pythagorean triplets, we know that we really don't need to solve for these angles. We have a 5 here for our hypotenuse, and we have a 4 here for one of the legs. Haha! Pythagorean triplet right here, boom baby, 3, 4, 5 triangle. So we know that our relative velocity is pointing directly east at a speed of 3 meters per second. And if we want to solve this entire problem, we know that this is 600, and we can even bring in that previous fifth kinematic equation, which is V equals d over t, t equals d over v. Now we have our time is equal to 600 divided by 3, which is equal to 200 seconds. And if we just look back at our slideshow, huzzah, please click. We do have the option of 200 seconds. So yeah, the main thing to take away from this is that The concepts are really easy for the F equals ma competition. It's just physics 1. There's no weird electrostatics or thermodynamics or any like modern physics, quantum mechanics. There's nothing like that. It's just physics 1, which is relatively easy compared to some other things. However, it takes a very advanced approach to it, where it twists these into very high level looking questions that look really intimidating on hard. And I slowly started to realize that as I was making the presentation, but I kind of got too lazy and just did it anyways. So the main thing is to just dissect every problem into simpler components, just like you would with a regular physics problem, but with a much more advanced interpretation. And typically, I like to compare this with competitions like the AMC, the American Math Competition, I think, and the USICO competition, which is the USA Computing Olympiad. And it just feels really similar because it takes these very simple math or coding or whatever concepts and just makes it very complicated looking and very intimidating. But in the end, it's just based on these very root concepts that we all learn about. So I guess that's kind of the main takeaway that I want you guys to all learn from this. And just remember not to be too intimidated and just to work through these really calmly. And on that note, I just want to thank all of you for attending this. If you thought this felt really hard, really intimidating, please let me know. And I'm most likely going to change how I'm going to teach this class because this class, it was mainly just like me talking, and I didn't get as much of the kind of user interaction that I really wanted. So I think next meeting I'm going to have a worksheet, and how this online thing is going to work is I'm just going to get through the basic concepts, and I'm going to put the worksheet up, probably link it in the description or in the comments, and then just have you work on it, or I'll just put it in the folder, and then I'll work through it after a while. Alright, thank you so much for attending. I'm so happy that I got to teach you guys. I'm sorry, this is my first recording, and I really don't want to record another 1 hour and 20-minute recording. So, forgive my mistakes, please, and I hope you enjoyed, I guess. And stay tuned for next Wednesday. Alright, thank you so much. Have a great day, and I hope we have a great time learning physics together. Thank you. Goodbye.